So our last set of slides, introduced the idea of special relativity and how the speed of light is a constant value. And the Michelson-Morley experiment, which actually verified that, even though they didn't realize that's what they were doing. Michelson, by the way, once he read Einstein's work, agreed that his experiment, in fact, was working properly and did, in fact, agree with Einstein's relative motion and special relativity. Morley didn't quite accept that, and so Morley spent quite a few years later trying to replicate the experiment with greater detail and did not fully accept the results of his own experiment. Hence, Michelson became more famous than Morley, because it turns out Michelson and Einstein were actually right about this. So a consequence of this is something that we call the time dilation. So imagine you got a spacecraft. You've got a laser that goes from one side of the spacecraft to the roof of the spacecraft, then back down. So that takes a certain length of time. So it takes a time to go up and a time to go down. So this will be called, I'll call that like 2 delta t. So delta t is the time it takes to go up and down. Now, if the spacecraft is actually moving, then when it reaches the top of the top of the spacecraft is way over here, so light really traveled a much longer distance. And then coming back down, instead of coming straight down, by the time it gets down to the bottom, the spacecraft has moved over to there. So this is a much longer distance than just going up and down. And so that's going to take longer. Now, Einstein said that yes, it takes longer, so someone standing here watching it will see a longer time pass. But he said that if you're in the spacecraft going at constant speed, you can't tell that you're in a spacecraft going constant speed, so you would see precisely the same thing that you saw before. It would look like it went to the top and went back down. And so you would measure the same time that you did before. And so that would mean that you would actually measure less time passing than someone who was staying stationary. And so this idea that you'd measure less time, he went one step further. And he said that means that less time passes for you. Not just that you measured less time, but those less time passing. So that means if you got the spacecraft going, then you might measure that time to be a certain amount of time. Someone else measured quite a bit longer. Well, consequence of that is imagine a spacecraft going very close to the speed of light for a very long time. This is called the twin paradox. So this is kind of a hypothetical thing that you have a pair of twins here, and they're exactly the same age. One gets into a spacecraft and then flies for 10 years and comes back to Earth at near the speed of light. So 10 years have passed. So that twin is 10 years older. But his twin brother might be 40 years older because 40 years passed. And so one of them 10 years passed, one of them 40 years passed. Now, Einstein said, in fact, that this is exactly what happened, that more time passed for one than the other. Okay, this is time dilation. So the faster you go, the slower time passes for you. Okay. So that means you don't experience as much passing of time. Now, Albert Einstein wasn't the only one working through the math of this sort of thing at the time. So Henri Poincaré, a French mathematician, was doing the same thing. Now, Poincaré, however, thought that these measurements of time were kind of like an illusion of some sort, that time is an absolute thing. Einstein accepted that no, both of them literally experienced different times. Not just that they felt like different time, but it really was a different amount of time for each one of them. It wasn't just a measurement, wasn't just a feeling, it really was different. And Poincaré did not accept that. Poincaré came to the same mathematics, but thought it was some kind of measurement effect. And so what we realize is, well, which one of them is more famous? Okay, it's because Einstein was right. Poincaré was wrong. This was, in fact, a real effect, not just an illusion. So Einstein was correct in his interpretation. This means that time is, in fact, not an absolute quantity. Time is relative. It's relative to the observer. It's relative to the motion of the observer. Okay. This also relates to another issue that we have, and that is that if you imagine a spacecraft and light traveling from one end of the spacecraft to the other takes a certain length of time. If the spacecraft's moving, by the time the light gets to the front of the front of the spacecraft is over here somewhere. So by the time the light gets there, the front of the spacecraft is further over here. So it takes light a lot longer to get to the front of the spacecraft because the front of the spacecraft keeps moving as the light's traveling. So light must take longer to get there. Now the problem is this is a linear effect right here. The equations for time dilation are not linear. So that means that something has to give here. In fact, the square roots and squares in the equation. So something has to give, and what gives is the size of the moving object has to shrink. And so that means in order for the time to work out the same, because if you're inside the spacecraft, you don't see the motion, so you think it takes the same length of time for light to get from the back to the front. Whereas someone watching sees it take longer. Well, time's running slower for you, and so that means that that to get from the front to the back in that same length of time, you actually have to be smaller. And so the faster you go, the further you shrink. That's called length contraction. So, faster you go, the smaller the dimension. Got a train moving a certain speed? If it's sitting stationary, if it's moving, it's actually shorter. Okay, so length contraction, which means that space is also not an absolute quantity. Now, of course, there's equations that describe all this stuff. And those equations are going to be what gives the mathematics and the mathematical basis. There are tests of all this. Cosmic rays hit the upper atmosphere and cause particles to come raining down to the earth. The problem is that the particles don't live long enough to make it to the ground, and the distance is too great. But one of the things we discover is because of the contraction of space, they actually make it to the ground after all. And I know they do because this was a project I did as a senior undergraduate physics major, was measuring these cosmic mu mesons making it to the ground. Another test of time dilation was done by using an atomic clock. This is one of the most accurate possible clocks. I mean, the atomic clock will keep accurate to within a second within 1,000 years or more, thousands of years. And so an atomic clock circling the globe was going faster than one sitting stationary. And so when they compared the two, the one that was moving was actually lagging behind the one that was sitting stationary. The one sitting stationary was actually a little bit ahead because time was passing slower for the moving one. If you do not include the effect of time dilation, that means a GPS satellite fix would be wrong. It would actually give your position off, and it'd be getting farther and farther off the longer the satellites are up there. So you have to compensate for that. That's done electronically in your device. When it takes the GPS fix, it does the calculations for you already. Now we get to the equations, and that will be our next topic to study are these equations.